Okay, today we talk about valence electrons and bonding, and Lewis dot structures will come next. Okay, Lewis dot structures. But valence electrons, let's talk about valence electrons. Here I have a picture on the board of the periodic table. And as you know already, we have talked about the fact that the s orbitals are over here. These are the s orbitals represented by these elements. And of course, the third and fourth electron, the 11th and 12th electron, the 17th and 18th electrons, and so on. So that's 37, 38. Those are going to be living or existing in the s electrons. Over here, right, we have the p orbitals. And so these number of electrons, let's say we have arsenic here, 33, okay, the 5th, 6th, 7th, 8th, 9th, and 10th, as well as the 13th through 18th and the 31st through the 33rd, electrons will be in the p orbital. What are these ones again? You remember down here? Yeah, these are d orbitals. And d orbitals are, they are never the last ones to be filled. Now the reason why this is a 3d orbital here, and this is a 4s, and this over here is 4p, these numbers are important right here. Those are that's the first quantum number, right? And that represents the energy level. And so these orbitals, technically, they get filled after the 4s, but technically, they are on the third energy level. And valence electrons, okay, are the electrons, and you can write this down, the electrons that exist in the outermost levels of the atom. And of course, when we talk about outermost levels of the atom, I'm going to put in there too, we're talking about the sublevels, right? Or the orbitals. So the outermost levels of the atom. Okay? These electrons are found in the s and p orbitals only. So as I began to mention here, and I'm going to just erase this stuff here so far, but as I mentioned here so far, the s and the p orbitals in any row, the s orbitals and the p orbitals are always on the highest energy level. And even if we take a look at the lanthanide series, okay, protactinium here, let's say this, take a look at this one right here. This is in the 4f orbital, right? So what number is that? That's number 59. So we fill the 6s orbital, then the 4f orbital gets filled. But what's the outermost orbital, or the highest energy level is 6, right? So 4 is, yes, it's filled after the 6s, but you look at these numbers and you realize that the largest energy level orbital, that's the outermost, okay? Those are the ones that are exposed. So when we talk about valence electrons, they're the outermost electrons. Consequently, these electrons are the ones that are involved in bonding. So we talk about ionic bonds, right? That's due to opposite charges and electrons being transferred. Those electrons involved in bonding are the valence electrons. So let's add that to our notes. These electrons are also the ones involved in bonding. So chemical bonding, of course. And we're just going to, well, what we're going to focus on is ionic bonds, right? Because that's pretty easy to see how electrons are transferred to make ions, and then the opposite charges get together. We'll talk a little bit about covalent bonds too, and obviously electrons are involved there as well, but it's not the ionic charges that determine how they combine. So we're going to focus on ionic bonding for now, okay? Ionic focus. And that'll just kind of make things a little bit easier. Okay, so valence electrons. These are the electrons that are involved in bonding. They're on the outermost electrons, outermost shell. The maximum number of valence electrons in any energy level Actually, let me go back to a question you did in your textbook there. Do you remember that question about how many sublevels in level X? Okay. Did anyone recognize the pattern there? Like how many sublevels in level 1? 1, just the 1s. How many sublevels in level 2? 2. In level 2, there's just 2. It's the 2s and the 2p. There's no 2d. There's no 2f. 2 sublevels. Remember, the p orbitals are 1 sublevel. There's 3 distinct p orbitals, but they are degenerate, so they're the same energy. That represents 1 sublevel, the p sublevel. Okay? So there's the 2s, and then there's the 2p, so 2. 3, we have 3s, 3p, and 3d. There's a 3d sublevel. Okay? 4. 4s, 4p, 4d, and 4f. So if you look at that pattern, if it's x sublevel, okay, how many sublevels in energy level x? There would be x sublevels, the same number. So in energy level 1, there's 1 sublevel. No, okay, good question. We can't see everything. You can only take a look at really the first 4 energy levels to get that pattern. Okay, good question though. In 5, is there only 4 as well? That's all that's represented right there in the periodic table. But you got to understand that there may be more elements discovered. There may be more. You know what I mean? So the pattern is that for the sublevels, they're the same number of sublevels as the energy level. So that's the answer to that question. Okay. All right. But in the s and p orbitals, how many electrons can exist in any energy level if we're just considering the s and p orbitals? So let's take a look at the 3s here and the 3p. How many electrons could, if these were full, how many electrons are we talking about? In the 3s and the 3p, we have 1, 2, 3, 4, 5, 6, 7, 8. Remember, the 3s can handle 2, the 3p can handle 6. So 2 plus 6 is 8. So we can only have a maximum of 8 valence electrons for any element. We better write that down as well. There are a maximum of 8 valence electrons for any element. Now I'm just going to move this diagram down a bit more. Oh, can't do that. Oh well, I can't. This messes with me. Alrighty. Okay. Okay, so when we're talking about any energy level, there's only 8 electrons that could be in the s and p orbitals. So when we talk about identifying these electrons, like let's say phosphorus here, number 15, okay? How many valence electrons does phosphorus have, the atom phosphorus? So how many s and p electrons does it have in its outermost level? Any guesses? 5. Let's see. The outermost level would be this one, right? 1, 2, 3, 4, 5. Beautiful. That's exactly right. So phosphorus has 5 electrons. What do we know about the phosphide ion? What charge is it? -3. Okay. The phosphide ion is -3. Now what does this mean? What does the -3 mean? Okay, it likes to pick up 3 more electrons to make it an overall charge of -3. So 3 more electrons would go here, here, and here. Okay, that's interesting. Let's take a look at some other ions. What about fluorine? Right here, fluorine. So fluorine, the fluoride ion, is a charge of what? -1. Okay, so that means it has how many s and p electrons? How many valence electrons in the fluorine atom? 1, 2, 3, 4, 5, 6, 7. And so if it's a -1, it means it likes to pick up 1 to make 8. Phosphide, or phosphorus, like to pick up 1, 2, 3 to make 8. Okay, now if you look at that, at all the other atoms and all the other ions that can be made here, like even beryllium. Okay, let's take a look at beryllium. It's on the other side of the chart, right? So beryllium has how many valence electrons? Just the atom of beryllium, it has 2. Okay, good, you guys are getting it. Now what ion does beryllium like to make? In this column here, this family. Okay, 2 plus, right? Okay, so that would mean it likes to give away this electron and this electron to be like helium, to have the same valence electrons as helium. So what I want you guys to notice here is that these noble gases are important. Phosphorus picks up 3 electrons to be like argon. Right? Fluorine picks up 1 electron to be like neon. Beryllium gives away 2 electrons to be like helium. Okay? Yep. Remember that these, roughly around here, right? These guys are the metalloids, and they sometimes act like, non-metals. Sometimes they act like metals. That's kind of their nature. But if we talk about aluminum, it has the choice to give away 3 electrons or to pick up 5. So it's going to give away 3 to become Al3+. Okay? So the bottom line is that in forming ions, it's the valence electrons and it's the outer shell. It's called the outer shell that gets filled. Okay? Each atom wants a full outer shell in order to be stable. So that's why it picks up some electrons to fill some holes, or it gives away some electrons to still have a complete outer shell. Okay, so let's just jot that down for notes. Okay, so we talked about ion formation here just now, so these notes here just say, in ion formation, atoms either pick up electrons or give away electrons in order to have a full outer shell. So like we said, chlorine would pick up 1 to become like argon, and it would have a full outer shell, and so on. Magnesium would give away 2, so it could have a full outer shell like that of neon. Okay? Now, electron dot structures. Let's talk about electron dot structures. In your textbook, they may be called electron dot diagrams. You may hear them. You may hear me call them electron dot structures. That's just another way of talking about them. But electron dot diagrams, what they do is they show the valence electrons for an atom. And as we know, these valence electrons are involved in bonding. So let me just pause there for a second. If we're talking about fluorine, okay, an electron dot diagram uses a series of dots surrounding the symbol to just identify the valence electrons. So fluorine, the fluoride ion would have, it's a -1, right? So the fluorine, if we're talking about just fluorine, how many valence electrons does it have? Just fluorine on its own? Yeah, see, look at it's number 9. Let's go back to the diagram. So it's number 9 here. So it has 1, 2, 3, 4, 5, 6, 7. Okay. So if we're just talking about electron dot diagram for fluorine, it would have 7 electrons. So you usually start on the right side here. 1, go to the top, go to the other side, 3, go to the bottom. Okay. I'll talk a little bit more about this order. Okay, and people do it a little bit differently, but you basically, your dots, you kind of envision 4 sides of the symbol, and you put dots on every side, and each side can take 2 dots, and that would give you 8 in total for a full shell, see? So 1, 2, 3, 4, 5, 6, 7. So that's how you would show fluorine. Let me just get rid of that square. So that's how you would show the electron dot structure or diagram for fluorine. Notice that it has 1 space here available for one more electron for its outer shell being completely full. Okay? So 8 dots around the symbol would represent a full outer shell. And actually, this right here would represent the fluoride ion if it has 8 dots around it. Okay? All right. So let's go back and let's talk about bonding again. Okay? So if you have fluorine here and it's got 7 valence electrons, you can see that it's really wanting one more valence electron. So we'll go back to the periodic table. All right, F has a -1. Did you know that sodium and fluorine really like to get together and form an ionic bond? And do you know why that is? Because sodium over here, and A, it has 1 valence electron. Okay? And so fluorine eyes this electron up and says, hey, I want a full outer shell. And it says, sodium, don't you want a full outer shell as well? Because if I got rid of this, you would have a full outer shell. You would be like, neon. And so basically, that's why they form a bond so easily. And you could actually draw it like this. And A on here. And then its electron slides in there. And that is how you would draw the electron dot diagram for the compound sodium fluoride, NaF. Okay, so it's sort of an easy way of showing the electrons. I don't know if I mentioned this before, but that full octet, let's see, full outer shell, okay? Just going to add to these notes up here. This is called the octet rule. Okay, so octa is 8, and it's a rule that it's at it's kind of the most, I want to say, comfortable position, the most peaceful, the lowest energy sort of position is to have a full outer shell. So that's what these elements are trying to attain by bonding. All right. So what else do we know? Talked a little bit about this already. The valence electrons are the ones that get lost. Okay, when a positive ion forms. Okay, so they're the ones that leave. The extra electrons, they're the ones that leave. Okay. And electrons fill these outer sublevels when negative ions form. Okay, so there's electrons that fill the outer shell. We already talked about this. I don't know if you've actually written this down yet, but again, here's some notes here about the valence electrons being the outermost electrons in the atom. Okay, so a little bit of summary of what we've talked about here. Make sure you got that down in your notes. All right, so have your periodic table handy there. We talked about sodium, aluminum. Okay, so aluminum. If we're doing drawing electron dot diagram for aluminum, okay, you look there. It's got 1, 2, 3. Right? It's got three outer electrons. Now, on this right side here, and I think the textbook does it like this as well. Generally, this side here is the s orbital. All right? It doesn't have to be on the right side, but typically, if you're just doing electron dot diagrams, this is the s orbital. So notice that the s orbital for aluminum is full. Okay? And we also have 1 electron in the p orbitals. And so over here, these other 3 sides, I like to view them as the p orbitals. So p whatever, px, py, and pz. This is not, I don't think this is a global standard by any means, but you'll see this in the textbook. That's kind of how they do it. But it was mentioned earlier about orbitals And we talked about hybrid orbitals earlier, which we may get into in this course. I'm not really sure. Probably I'll mention them again later. But when we have a situation like this where these two s orbitals are, these two electrons in the s orbital are happy in this s orbital, and let's say you have something like, let's see here, if we have silicon, we have 1, 2 in the s orbital, and then we have 1, 2 here. Okay, so silicon. All right, silicon. This is an example of half-filled orbitals. If you can have all the orbitals represented for the valence electrons, if all of the orbitals can be half-filled, that's actually that's actually preferred. Like it's kind of the lowest conflict. You can see these two electrons are shoved in this s orbital. The p orbitals are a bit higher energy, but really not much. And so what you see happening is one of these electrons could actually jump over here and fill this spot, so that all of these orbitals are half filled. And this is sort of where you get into hybrid orbitals and things like that. And so this is something that can happen so that silicon can bond, a certain way. So we're not going to talk about hybrid orbitals right now, but just suffice it to say that the valence electrons should be distributed out here. And your s orbital fills up first, and then remember 1 dot in each of the p orbitals. So let's just go back and take a look at something like gallium. No, let's not do gallium. Let's do tin. Okay, tin, Sn. Look back to our periodic table. Tin is right here. So we have 1, 2 in the s orbital, and then 1, 2 in the p orbitals. So those are your valence electrons. There should be 4. So tin is a lot like the silicon one we just did. So 1, 2, 3, 4. And that's how you do tin there. Okay. So let's take a look at chromium. What about chromium here? It's got some electrons in the d orbital, 3d orbital, but remember the valence electrons are only the s and p. So how many valence electrons does chromium have? 2 is correct, yes. It just has 2, these 2 right here. Okay, these ones don't count. They're there, but they don't count. So if we're talking about valence electrons, chromium just has 2, like that. So all of those elements in the d orbitals there just have 2. What about the ones in the f orbitals down at the bottom? Well, f orbitals are filled right here and right here. And these are f's, right? 4f and 5f. So how many valence electrons do these guys have, like uranium? Just 2. Yeah, that's these electrons right here. So on your periodic table, if we go back to the intro, here we go. This is the periodic table that you guys have. You notice, and I'll get rid of all this. You notice that chromium has a 3 plus and a 2 plus charge. So remember, this is the ion, and with the d orbitals and f orbitals, there's some really weird things going on because there's lots of conflict, there's lots of orbital overlap. So the electron dot diagrams are really just for very simple sort of ionic compounds, you know what I mean, with this area and this area over here. Once you get into the transition metals with multiple oxidation states and stuff, then you start talking about electrons jumping from energy level because, in order to bond, they like to have some more available bonding spaces, or, the difference in energy level between this d orbital and this s orbital and this p orbital is quite small, right? The difference is very, very small. So you will have in certain situations, these guys right here especially, right? Electrons will be jumping back and forth to make some of the d orbitals, d electrons might jump into the p there to make some more bonding sites, sort of thing, right? That's the best way I can explain it. So the multiple oxidation states here, transition metals, they behave just a little bit differently because there's a lot of electrons that are very close to an energy level, and they form some hybrid orbitals, or just the electrons jump into available s or p orbitals. So yeah. So this electron dot structure is kind of meant for just simple bonding and simple understanding of how the electrons behave. You got to remember when we're talking about quantum mechanics, electrons, they don't behave like regular particles. This is one of the best ways we can understand ionic bonding, and so this is a very simple model. So you're right, there are some more complicated, mathematics to to why these transition metals have different charges. But so the electron dots, we'll just kind of stick with the simple bonding. But let's do back here. So let's take a look at some compounds. Okay, for example, let's do a CaCl2, and let's represent this by electron dot structures. So CaCl2. Okay, what about Ca here? Ca has 2, right? And Cl has how many? 7. Cl has 7. Okay? So, and just take a look at the atoms, not the ions for now. Okay? So, if you look at this, Cl has kind of one bonding site. Calcium is, kind of okay with these electrons that fill in the s orbital, but as you know, okay, calcium likes to form a 2+ ion, chlorine likes to form a 1- ion. And if we look at this from the electron dot standpoint, this is what happens. Cl2, okay? So calcium has 2 electrons to donate, and each chlorine has 1 site to accept. So it would look something like this. Ca. Now this is when you're going to have to kind of move your dots around, which is totally fine. And I'm going to actually use just different colors here. So you have chlorine saying, hey, can I use one of your electrons? And calcium says, sure. And then another chlorine says, hey, you still got 1 left over there. For me, can I use one of your electrons? It says, sure. So you see that? So the chlorine has a full octet around it. Okay? And it's quite a hog for electrons. The term is electronegativity. It has a very high electronegativity. And so it likes to grab these electrons and pull it tight. But you can kind of see, right? Chlorine really likes a full octet. Calcium says, you know what? You can have those 2 electrons because really underneath the surface here, now that you've kind of taken them, I have an octet just like argon, right? So we'll go back to the table. Calcium is right here. This is getting messy, but it has an octet, a full octet just like argon now with these 2 extra electrons basically used up in bonding. Okay? So we get that? So that's your CaCl2. Okay, what about K2S? Why don't you guys take a minute and just draw that electron dot structure, K2S. See if you can do that. So here's your electron dot structure, your diagram for K2S. Notice that there are 2 Ks, that's what we need, and there's 1 S. And notice also that S has a full octet around it now that K has donated its electrons, right? And so because K donates its electrons to S, that's why we write, K has a +1 charge, because it gives away its 1 electron. So it has overall charge of +1, because it has 1 less electron. And then the S, we're talking about ions, it's a 2 negative charge because it likes to pick up 2 electrons. And so really we don't show the ions so much as we show just the electron, the valence electrons in bonding. So these are kind of different if you think about this, right? Because this has a full octet and this has a full octet. And so you'd think, why do they get together? Well, when we show it this way, it's because of the difference in charge. When we use electron dots, you see that there are empty spaces, right, that S wants to fill. And K has an extra electron that it would like to donate. And so it's a little bit of a different system, right? And so far we've been exclusively taking a look at, this, and that's why we need 2 of these to make K2S, right? This is what we've been doing here.